Have you ever stood in front of a massive hydroelectric dam and just wondered how it actually works? How it turns all that rushing water into the electricity powering our homes? Well, the secret is completely hidden inside the geometry of fluid dynamics. So let's dive into this explainer and decode the fascinating physics behind what happens when a high-speed jet of water strikes a moving surface.
Here's our roadmap for this explainer. We'll be hitting 5 sections. 1. Jets on curved plates. 2. Decoding velocity triangles. 3. The sine rule refresher. 4. Solving first-stage numericals. And finally, 5. Advanced problem applications. Let's jump right in.
All right, Section 1. Jets on curved plates. Setting the stage.
Okay, before we even touch the math, we really need to understand the physical reality of the mechanical components we're looking at. Picture a high-pressure jet of water blasting directly into a metal blade. In the real world, like inside those giant water turbines, the plates are almost always unsymmetric. Why? To squeeze out absolutely every drop of maximum energy. Because the entry and exit angles are entirely different, the water's behavior changes drastically as it travels across the surface. This means we can't just do one simple one-size-fits-all calculation. We actually have to analyze the entry point and the exit point as two separate but deeply connected events.
Moving on to Section 2. Decoding velocity triangles, the master diagram. So looking at this cross-section of a curved turbine blade, you can really see how the vectors map out perfectly. We've got an inlet triangle down at the bottom left where the water enters and an outlet triangle up at the top where it leaves. And you know, the lengths and angles of these lines aren't just random scribbles. They represent the exact speeds and directions of both the water and the moving blade. If you can read this diagram, you can basically solve any turbine problem out there.
Let's translate that alphabet soup into plain English, because knowing these 5 specific velocities is literally the key to unlocking every single problem we're going to face today. V1 is the absolute raw speed of the water jet, but because the plate itself is moving away at speed U1, the water actually feels like it's hitting the plate at VR1, which is the relative velocity. Finally, we break that absolute velocity down into 2 functional parts. VF1, which just pushes the water through the system, and VW1, the whirl velocity. And guys, the whirl velocity is the absolute magic ingredient here. It's the only component that actually does physical work and spins the turbine.
Which brings us to Section 3, the sine rule refresher, the mathematical bridge.
All right, we've got our visual model built and our variables defined. Now, we need a mathematical tool to bridge the gap between drawing nice triangles and calculating real, actionable numbers. It turns out, this simple equation isn't just a high school math throwback. It's your ultimate decoder ring for these velocity problems. It simply states that for any triangle, the ratio of a side's length to the sine of its opposite angle is constant. Since our velocity diagrams are literally just triangles, this brilliant rule lets us unlock missing vector lengths if we know the angles, and vice versa.
In practice, you're constantly going to be using this rule to cross-reference the known lengths and angles on the inlet side of the blade to figure out the missing variables on the outlet side. Because the water physically glides from the inlet up to the outlet, the relative velocity you calculate at the bottom becomes the absolutely crucial foundation for your math at the top. It's all connected.
Section 4. Solving first-stage numericals, putting theory to practice.
Let's take a look at problem 17.19 and get our hands dirty. We're given an absolute water velocity of 40 meters per second, and it's striking a vane that's already moving at 20 meters per second. We're also told we need the water to enter without shock. Now, this is a massive engineering requirement. If water enters with shock, it literally crashes into the blade, creating tons of turbulence and losing a huge amount of energy. Entering without shock simply means the angle of the blade perfectly matches the relative velocity angle of the water, so it just glides on completely smoothly.
Whenever you're hit with a numerical problem like this, just follow these 3 logical steps so you don't get lost in the weeds. Step 1, isolate your givens. Grab your V1 and your U1. Step 2, immediately sketch out your inlet triangle and hit it with the sine rule. Step 3, use the math to find that highly efficient, zero-shock entry where the vane angle aligns flawlessly with the water's relative path.
If we plot those numbers out, we get this really specific geometry. Take a look at the top outlet triangle here. Because the water leaves at exactly 90 degrees to the direction of motion, the absolute velocity V2 goes straight up. This precise 90-degree angle is an absolute gift for engineers. It means the whirl velocity component at the outlet instantly becomes 0, which dramatically simplifies all our calculations for the total work done.
All right, stepping it up a notch with problem 17.20. Once we know the geometry and the specific angles, we aren't just drawing lines on a page anymore.
Now we can calculate the actual physical force exerted by the jet onto the vane, and from there, the total work done per second. This is where the theory turns into real-world power generation. This is how we figure out exactly how much power our theoretical turbine is cranking out.
Mapping problem 17.20 out, you can clearly see how a 60-degree exit angle totally dictates the size of our vectors. Unlike that 90-degree example we just looked at, check out the top right here. We actually have an outlet world velocity this time, and it's pointing in the opposite direction. This opposing vector fundamentally changes the net force calculation, which in turn directly determines the final power output of the whole system. Seriously, every single degree of that curve matters.
Section 5. Advanced Problem Applications, Deflection Angles. Notice anything different about problem 17.21? We actually aren't given the specific inlet and outlet angles separately like we were before. Instead, we're given a total deflection angle of 120 degrees. Think of this as the total angle that the water is bent as it travels its entire path across the moving plate. This diagram beautifully captures the physical reality of that deflection. Look closely at the geometry here. A 120-degree total deflection literally forces a very specific relationship onto our inlet and outlet triangles. Because we know the vane is symmetrical, we can use that 120-degree total bend to mathematically reverse engineer the missing individual angles at both the entry and the exit points. It's like solving a giant puzzle.
Okay, our final challenge, problem 17.22. This one requires synthesizing absolutely everything we've just learned. We've got a 12 meter per second jet, a 5 meter per second moving vane, a 120-degree deflection, and a strict mandate for zero shock at the inlet. We have to calculate the absolute velocity of the jet at the exit, both magnitude and direction, and figure out the work done per unit weight of water.
By carefully sketching out this final master diagram and systematically hitting it with our sine rule, we piece the whole thing together. We use the 120-degree deflection to find our relative angles, trace the relative velocity from the bottom triangle straight up to the top, and pin down the exact optimal entry angle to extract the absolute maximum work from the system. It really is a perfect cascade of geometry and physics working together.
As we wrap up this explainer, I want to leave you with a bit of a provocative question. We just used some brilliant math to perfectly align vectors for zero shock and maximum work. But in the messy, real world of engineering, water has friction, vanes have microscopic surface roughness, turbulence is pretty much inevitable. So how do engineers actually bridge the gap between the elegant, perfect math we just mastered here and the chaotic, high-pressure reality of a spinning hydroelectric turbine? It's a fascinating challenge, and definitely something to ponder until next time.